Hello, my name is Sarah and I am a virtual employee of Business Conference Facilitation. Hope you all are as excited as I am about the conference. Basically, I am gonna be supporting you and following all your steps during the event. The conference includes several speaker presentations, Q&A sessions, coffee breaks, and a panel discussion. After each speaker, we are gonna have a 5 minutes long Q&A session where all of you are able to ask the presenter any questions regarding the topic. In case you want to ask some questions, just write him down in our public chat. There is a possibility to write him down during the presentation or as soon as the speaker has finished the topic and is ready to start the Q&A session. As you can see on the left, besides public chat there is a private one as well. In case you have some troubles with the connecting, sound, video, or other technical related problems, do not hesitate to contact us through private chat or call us directly. Here is a small tip on how to solve your technical issue quickly. We kindly ask you to 1. Refresh your browser page. 2. Try to switch your devices. 3. Re-log in into your account. 4. Check the internet connection and try to use your mobile internet. 5. Call us through the phone and we can give you an external link. There is our contact number above the screen. Please note that the recording of the conference and all additional post materials will be available within 10 working days after the event and our team will send it directly to your email. I wish you a wonderful conference and networking with the industry experts. Hopefully, I will see you soon during our upcoming events.
Ladies and gentlemen, welcome to our BCF event. Please let me know if you can see me and hear me well by writing down in the chat. Perfect. Since everyone is here, my name is Valerie Newman for the people from you who weren't yesterday, but are here today, and I will be your moderator for today's event. If you're facing any technical issues, I would like to remind you to kindly address them to my colleague Sarah, who is going to provide you with prompt assistance. I would like to officially welcome you to second day of e-motor technology conference. Allow me to move on to the program for the day. So first we're going to begin with session 4, self-communicated motors, AC, DC, electric motors. And we're going to have our first speaker, Dr. Ajay Punjay Pai, who is Principal Application Engineer and Technical Marketing at Infineon Technologies AG, who is going to present at optimization of efficient automotive drivetrain by smart choice of power semiconductors. Then we're going to continue with Mr. Jose Soler Vizan from Taos Technology, who is going to present the future challenge of rare earth permanent magnet synchronous motor. After a small, approximately 10 minutes coffee tea break, we're going to move on to session 5, thermal management for e-motors powertrains. And we're going to have our third speaker, Mr. Florian Rocht, who is a strategy consultant at InProcess, who is going to present at software-defined vehicle, the third generation of cars. And last but not least, we're going to have Mr. Srinivas Mavampalli, electrical motor actuator driver researcher at Eaton, who is going to present on pole changing induction machines for starter generation applications. Finally, we're going to have a panel discussion on topic gas oil price increasing influencing the e-motor technologies. And we are going to have Mr. Luca Castellini, who is an independent contributor, joining us for the panel discussion. So as you see, today is a day filled with information. And before we move on, I would just like to kindly remind you that you're going to receive all past conference materials, which include a list of attendees, a recording of both days, and all speakers' presentations in a PDF file in approximately 10 working days after the event. So now, we can move on to session 4, self-communicated motors, AC, DC, electric motors. And our first speaker for the day, Mr. Ajay Punjay Pai, Principal Application and Engineer Technical Marketing.
Hi.
Hello. Hi, do you
Hi.
hear me?
Yes, I can hear you. Can you confirm if you can see me clearly and also hear me?
We hear you and we see you very well.
Okay, perfect.
I can
So
see your
then,
presentation.
yes, I'm sharing my screen. I hope you can see my PowerPoint in full screen.
Yes, I see it. Yes,
Okay.
thank
Yeah.
you.
Then also welcome from my side to this eMotors Technology Conference. So my name is Ajay Punjal Pai. So the last 8 years, I'm employed at Infineon, where we are trying to solve the problems in the automotive market with our power semiconductor technologies and modules, specifically silicon carbide. And today I will show how we can benefit from these powered semiconductor technologies and modules in automotive drivetrain applications, and how we can optimize these drivetrain or powertrain applications. So as we all know, e-mobility is a very promising market for power semiconductors, power electronics, and therefore we see a lot of companies jumping into this market. And if you look from the commercial side, of course, power semiconductor market is around $20 billion as per the 2020 report of Strategy Analytics. Of course, it's 2 years old already. And the automotive market is 40 billion US dollars. And the automotive power semiconductor market, I mean, in comparison, it's 10 billion US dollars. Of course, it's smaller compared to the normal automotive market. But important to see is that the total semiconductor content, if you see a compact ICE car today or an internal combustion engine car today, this is more or less in the range of 100 US dollars. But when we go to a battery electric vehicle, this automatically goes in the range of 1000 US dollars, sometimes even more. And this means that this automotive power semiconductor market is only growing exponentially in the next decades. And also from the technical side, the automotive applications are very important because they need high efficiency, typically in the range of 96%, of course, depending also on the application within the automotive, let's say, within the car. And also the failure rates are really super low. I mean, we are not even talking of parts per million, but rather parts per billion. So this means there is very low room for failure in the market. And also because the car can drive somewhere in the deserts of the Middle East or somewhere also in Siberia, they have to be designed and they have to withstand a wide range of temperatures. So this means the power semiconductors should function very well all the way from -40 up to 50 degrees Celsius ambient temperature. This is not the junction temperature, ambient temperature. And also from lifetime point of view, I mean, we buy a car normally unless we want to upgrade it, we use it for at least 10 years or so. And 15 years is normally the design lifetime of a car. And moreover, the space, the weight, all of this has to be optimized because there is only a limited space within a car. And making it bulkier only makes it less efficient. So therefore, e-mobility, I mean, I can confirm that e-mobility is going to be a super interesting application for power electronics. And when we look into the e-mobility application, so we see here a typical schematic of a typical car. So you see mainly a high voltage battery. So all battery electric vehicles normally have a high voltage battery, more in the range of 400 volt, but today also going fast to 800 volt systems. And this is supplying the energy in that case. And we see a high voltage bus. And from here, we have the power which goes to the motor and then to the wheels. And because the power output of a battery is DC, we have to invert it or convert it to AC so that the motor can run. And this is the task of the traction inverter. Of course, traction inverter also plays the role of controlling and accelerating or decelerating depending on the user input. And from that point of view, traction inverter is like the brain of the car, and in some ways also the muscle of the car. And of course, there are some additional systems. I mean, if you have a battery, you need to also be able to charge it. And normally it is done either by a onboard charger, which is a small AC-DC converter within the car. And from there, you can directly charge from the grid. Or you can also charge with an off-board charger, where you get a DC input and you directly feed it into the high voltage bus. And of course, all battery electric vehicles also have a small 12 volt or some cases 48 volt battery, because you need some supply for the control and for the protection circuits. And therefore, you have a low voltage battery, and to have a flow of power between the high voltage and the low voltage side, you also need a small DC-DC converter. And here you can see on the left side the power ratings of the different components which I just mentioned. But from the size and from the amount of power it has to handle, you can see that the main inverter, or also known as traction inverter, is the biggest component from power point of view. And therefore, this is also very important. And I will explain this in the next slide. If you take a typical battery electric vehicle, such as Volkswagen ID, for example, or any battery electric vehicle for that matter, and look into the powertrain and make a rough estimation of the power losses in the complete powertrain, you see that around 40% of it is coming from the battery alone. Yeah. And then roughly 30% of the power losses are coming from the inverter. This means after the battery, inverter is one of the biggest power loss sinks in the electric vehicle. And therefore, we have to optimize this inverter in order to have a successful car. And what does this application look like? I mean, those familiar with power electronics already see that this is a B6 bridge. It's a 2-level inverter topology, voltage source inverter topology. And today the power levels are somewhere between 100 to 300 kilowatt. Sometimes cars also have multiple axles. So this means you would have a small inverter in the front and a small inverter in the back, or it can be sometimes also single axle. And the DC voltages or the battery voltages are between 400 volt and 800 volt. Of course, most of the systems today are around 400 volt, but this is fast growing towards 800 volt. And the switching frequency is not so high from a power electronics point of view. It's more or less in the range of 10 kilohertz. And this is, like I mentioned here, it's a hard switching application. So no resonance, no LLC topology or something like that. And you can see here also a picture of a demo inverter, which we built at Infineon, just to give a rough idea how it looks like. And like I mentioned, inverter is going to be the key for a battery electric vehicle. And this means if you consider the inverter, one of the main components of the inverter is the power switch itself, or the power semiconductor itself that you see here. And therefore, optimizing this power semiconductor will be really key to making a successful battery electric vehicle. And this is why we will focus in this lecture on power semiconductors. Okay, let's look at some of the popular battery electric vehicles. I'm sure all of you have seen a few of these on the roads. Tesla Model 3, Nissan Leaf, one of the best-selling electric vehicles. Also, Renault Zoe, very popular. And then the recently released Volkswagen ID.3, which is already on the market for a couple of years now. And if you look at them roughly, I mean, let's not take these numbers very seriously, but just to give you a ballpark, most of these cars, of course, Tesla Model 3 is an exception here, but most of these cars have to be in the range of 30,000 euros. And this means it's the base model. Of course, you can also add a lot of features, add battery capacity, add inverters and so on, and then it becomes expensive. But the base models are around 30,000 euros. And most of these offer around 100 kilowatt of power on the wheels. And for a WLTP emission profile or a drive cycle, we see around 300 kilometers of range. And most of these cars, they can accelerate from 0 to 100 kilometers per hour in roughly, somewhere between 8 to 10 seconds. Again, Tesla Model 3 is an exception. And most of these cars, they have a battery somewhere in the range of 40 kilowatt hour. And most of these cars, they weigh around 1,500 to 2,000 kilograms. And like I mentioned, they have to withstand 15 years of lifetime, including all safety features and so on. And why is this important? So if you look into the key parameters for battery electric vehicles today, you will see exactly these parameters that I just mentioned. And of course, today, one key selling point of battery electric vehicles, apart from the cost or the price, is the range, because customers have anxiety on how far can I reach with my car on a single charge. And therefore, range is a key selling parameter of the car. And to optimize range, we have to optimize the power semiconductors, the motor, the battery, and so on, because we have a limited charge and we have to get the best range or travel the highest distance with this charge. Let's look at how these parameters translate into inverter requirements. So you can see that the price, of course, it defines to some extent the cost of the inverter. And from the range, we have a rough idea of how efficient the inverter should be. And from the kilowatt rating of the car or of the powertrain, you know what should be the chip size, which should be in the power semiconductors. And also the acceleration. So the acceleration from 0 to 100 kilometers per hour, how many seconds are needed? This is directly having an impact on how much chip size you need inside the inverter. So if you need much larger acceleration, like 3 or 4 seconds, then you need much more semiconductor content, because the semiconductors there, they will face a very aggressive driving pattern. And also the mass has an impact on the dimensioning of the inverter, because when it's more mass, you need more torque, you need more power to push the car. And of course, robustness is something we can never underestimate in automotive, because robustness is really key. And this is where we place at Infineon the most focus on our power semiconductors. But there is also a kind of interdependency between these 4 or 5 parameters that I showed. It's not so straightforward. So dimensioning of the chip size has a direct impact on cost. And dimensioning also has a direct impact on robustness and on efficiency as well, because when you dimension it larger, typically you can make it more efficient, but then it gets more expensive and so on. So there is a matrix of interconnections, and it is very important to understand all these trade-offs to be able to decide and design the right system for a battery electric vehicle. So this means optimizing the power semiconductor is really crucial, and I stress this once again. This is where we try to bring in our expertise at Infineon. So inverter efficiency is normally rated over drive cycles, also known as mission profiles. And I'm sure all of you have heard of the NEDC and WLTP drive cycles, which are commonly used for benchmarking even internal combustion engines today. And if you look into a typical histogram of such a mission profile, you see that, so x-axis is the RMS current of the inverter that is used. And this is for an inverter with a nominal of 450 ampere RMS. And on the y-axis, you see the percentage of time the inverter is spending in this respective current. And you can see that around 450 ampere, which is the nominal rating, the inverter spends roughly 1% of the time. Whereas most of the time, more than 90% of the time, the inverter spends at less than 100 ampere, which is less than a quarter of the nominal current. So this means automotive traction inverters spend most of their time in light load, and therefore light load point is very important for efficiency. And therefore also parameters of the device at the light load and at low temperature is very crucial. Okay, this is a small video I made of a BYD taxi in Shenzhen, and you can see here the dashboard. Please pay attention to this side of the dashboard where you can see the power output of the inverter. And this was, if I remember right, up to 150 kilowatt of power. But you see that it's mainly driving less than 50 kilowatt. So even when the car is really pushing, accelerating hard, you see it goes up to 40 or 50, and seldom does it go to the rated power, which is 150. Therefore, this again confirms what I just mentioned in my previous slide. Light load point is very important for automotive traction inverters. Okay. But the inverter has to be dimensioned for the peak power. So if you look at the average speeds from the different mission profiles, you see that for WLTP, it's more 50 kilometers per hour. But if you look at the corresponding max speed, you have around 130 kilometers per hour. And for dimensioning the inverter, like I mentioned, what is important is not just the speed, but the acceleration that we do. And therefore, the automotive inverter has to be designed mainly for the peak acceleration. So therefore, dimensioning of the inverter has a direct impact on the cost. Also, dimensioning of the acceleration, so how much acceleration we need, this has a direct impact on cost. And here, the parameters of the devices, for example, RDS on or switching energy at the max temperature, junction temperature, which is typically 175, also going towards 200 degrees Celsius. This is very, very critical. So then what are some levers for optimizing a power module? Of course, we start with the chip. And here we have the chance to go to different technologies. For example, we can go to IGBT technologies, which is a bipolar device, or to a MOSFET technology, which is a unipolar device and therefore in many ways superior. And within a given technology, we can go for planar or trench, super junction sometimes, not so much for this application. So there are a variety of levers possible to optimize the power module. And outside the chip, let me stress here that the chip is not alone sufficient. We need a package, and the package also has to be optimized. And if you look at the package, the thermal stack of the package, how good is the heat conduction to a cooler? Also, what is the stray inductance, the parasitics of the module? How symmetrical are the power switches, particularly for silicon carbide? When you have to parallel multiple chips, how good is the symmetry so that the current sharing in dynamic and static conditions is very symmetrical between the chips? And of course, also producibility. How easily can we integrate mechanically and produce it in really, large volumes in millions per year? So these are really very important aspects of the power module. And therefore, optimizing the chip alone is not sufficient, but we have to also look into the power module, the package itself. And if you look into the chip technology, so you can see here the forward conduction characteristics of an IGBT in red and of a MOSFET in green. And you can see that in the nominal conditions, IGBT and MOSFET are more or less similar. In fact, IGBT is sometimes even better. And this helps in the dimensioning point, which is the nominal current rating. But in the light load region, in this green region, so the MOSFET is better because for a given current, it has a much smaller voltage drop, which is proportional to the current. But in case of an IGBT, independent of the current, you always have this fixed voltage drop. And therefore, MOSFET is better in light load conditions. So therefore, we have to really analyze what is more important for us to decide which kind of technology to choose. And if you look at the switching behavior, what you see here are the turn off waveforms. So green is current and red is voltage. So this is for an IGBT. But the moment you put a silicon carbide MOSFET, what is normally a tail effect that you see in IGBTs, this disappears in a MOSFET. So this means MOSFETs need or dissipate lower energy during turn off, simply because there is no tail effect during turn off. The same on diode reverse recovery. So when you have a silicon carbide Schottky diode mainly, which is a unipolar diode, so then you can significantly reduce the peak of the current when the diode turns off. This means you save some energy here. And this also reflects on the active switch, where you can see that the solid line, which is for a MOSFET with a silicon carbide Schottky diode, this has a much smaller peak. So this means you save energy in each of these switching events. And today, Infineon already has our trench MOSFET, so cool SiC MOSFET, released in the market since a few years. And this is based, like I said, on trench technology, which is known to be superior in terms of performance. And also, if you look at traditional silicon MOSFETs, trench MOSFETs are what nearly every companies today want to go, because this is really, in a given chip size, very super high performing. And with this, we have the potential to reduce the power losses by up to 60% in a realistic driving cycle. And this is something also many of our system designers confirm. So this means this reduced power losses automatically translates into range. And this means if you want to focus on range, then maybe silicon carbide is the right option for you. If you want to focus on cost, then it depends on what kind of battery you have. So if you have a small battery, then maybe IGBT is the solution for you. But if you have a really large battery, then I think silicon carbide pays off. So how can we help at Infineon? So at Infineon, we offer really a wide variety of possibilities. So from the technology, we offer silicon IGBT, we offer silicon carbide MOSFETs, we also offer super junction devices. And from the package side, we offer, starting from bare dies, we offer the chip standalone. Also, we offer a lot of variety of discretes. We offer frame-based modules like the hybrid pack drive. We offer easy modules. We offer molded power modules like the one you see here, which are also cooled on both sides. And this means the customer has really the chance to pick what they want instead of, taking what we give them. And of course, not to mention that we have different voltage classes and also different current ratings implemented. With that, I come quickly to the summary. Like I mentioned, e-mobility is really a very happening and a very promising application for power electronics, and I think we are all lucky that we have the chance to work in this domain. And automotive traction inverter is very, very important for a battery electric vehicle. And I summarized what are the requirements for an inverter application. But important is efficiency is graded at light load and dimensioning is done at the peak load. But range is determined more by the light load condition. That's why optimizing the efficiency in light load is very important. And we can optimize the power, the inverter with a variety of levers, choosing different technologies, but also optimizing the packages and so on. And Infineon is in a very unique position today to be able to offer really a variety of chip technologies, a variety of packages. And this means the customer can really choose what they want for their application. And with that, I thank you for your attention and look forward to some questions.
Thank you, Dr. Pai, for this great presentation. We already have a few questions for you, so let's move on to the Q&A session. And I will display the first one, which is, what do you feel is the net cost difference between SiIGBT and SiC MOSFET for automotive traction applications of, say, 200 kW? Mm-hmm.
Yeah, so what we have to really differentiate here is the cost or the price of the chip or the module and the system. So normally, I mean, if you look at literature, you can already see that silicon carbide is expensive compared to silicon IGBTs. I can also confirm that. So this means the power module might seem to be more expensive when you go for silicon carbide. But important is to offset this somewhere in the rest of the system. So this means when you go for a battery electric vehicle with roughly 50 kilowatt hour of battery, you might already be able to win some 5 to 10% range, additional range with the same battery when you go for silicon carbide. This means you get some more capacity out of the battery, and you are saving some money on the battery, and you might have to pay only a part of it for the silicon carbide. So even though silicon carbide is more expensive than IGBT, on the system, we have several confirmations from the market that this is helping them bring the system cost down. So therefore, it is important not just to see the cost of the semiconductor, but of the complete system as a whole. Because in the end, OEMs want to bring out cars which are more performance for less cost.
Thank you. Thank you very much for your answer. We received so many questions. Moving on to the next one. Why for larger batteries SCI is used and small battery IGBT is used?
Yeah. So this is again going to this trade-off between costs and, between the system cost and the power module cost, right? So when you use a silicon carbide module, of course, you pay more for the module because silicon carbide is more expensive, but then you want to offset this somewhere on the battery, right? So if you have a small battery, let's say you have a 10 kilowatt hour battery, and even if you can win 5% of additional range, this is half a kilowatt, if I made my calculations right. So half a kilowatt is less than 50 euros according to some figures available on the internet in the public domain, right? And this is something that does not offset or may not offset the silicon carbide. But when you go to a large battery, let's say you go to a 50 kilowatt hour battery, so 5% of the battery is already 2.5 kilowatt hour, and this is translating into a much larger, commercially much larger value, and this can offset silicon carbide. So this is why normally silicon carbide makes sense for larger batteries. And of course, I cannot tell you where exactly is this trade-off point, because this really depends on the system of the customer, how they design their system. It's dependent on the customer application.
Thank you very much for your answer. Now we have a longer question. I will display it in two parts. In slide 4, it is plotted 20% of the losses are coming from the e-motor and 30% are inverter.
Mm-hmm.
However, most efficiency maps of state-of-the-art BAVs tend to show better efficiency maps for the inverter than for the e-motor, almost for every point. Any comments on that one?
Yes, I think this is a very good comment. I can also confirm this. So the picture I had on the slide, this is more a rough number, right? Of course, we know that efficiency is really depending on what kind of conditions, driving conditions are existing, right? So therefore, the picture I showed, this is not, let's say, one average value. It's just a reflective value. It's, we should not take the numbers too seriously. But I just want to stress that inverter is key to this, key to designing efficient electric vehicles, because inverter is in between the battery and the motor, and all energy that goes through from the battery to the motor, this is multiplied by the efficiency of the inverter. So therefore, inverter is important.
Thank you. The next question is, do you think that for automotive, the mainstream will go from 400V to 800V or even higher?
Mm-hmm. So this is a difficult question to answer. I think this would need a crystal ball, and unfortunately, I don't possess such a crystal ball. But we see in the market that today, I mean, if you look at the distribution today, it's mainly 400 volt systems, and only a small portion of it, maybe 15-20%, 800 volt. And but we see a lot of focus on 800 volt systems because OEMs want to be able to charge their battery soon, and therefore when you go to 800 volt, you can reduce the charging time significantly, and this is why many OEMs want to go to 800 volt. But you have to also remember that there are different segments of classes, right? There is class A, class B, C, D, and so on, right? So if you take class A, a segment A or B, I think cost is really very, very important here. And normally the size of the cards are not so much. So therefore, you have to really make the cards super commercially very attractive. And from that point of view, I would think this will depend also on what is the class of the car. So if you look at class D or sometimes even class C cards, I think there it makes sense to go to 800 volt, but maybe not so much for the smaller cards. So therefore, I think there will always be a mix, but we really have to see if 800 volt systems will get more and more prominent in the future. So it's a question the industry has to see in the next years.
Thank you very much for your answer. Moving on to the next question. What is the market scope for GaN?
Mm-hmm. Yeah, so GaN is another wide bandgap semiconductor like silicon carbide. And of course, today we see GaN in a lot of devices. I mean, if you take a mobile charger, for example, you see already GaN there. You also see it in a lot of power supply applications, right? So therefore, GaN has really a lot of scope in the market. For automotive, maybe this is a bit early, but I think it will come at some point of time. So we have to see how it goes. But of course, GaN is also a very promising semiconductor.
Thank you. And the last question for the moment. What type of power semiconductors do you use?
I'm not sure if I understand this question right, but I think it's more what kind of power semiconductors we offer, right, at Infineon. So
we can ask the delegate to do some clarification on the question, and we can come back to it later. We are going to have a panel discussion as well at the end of the conference. You're going to join us, right, for the panel discussion?
Yes. Perfect. Maybe one comment just to answer the question the way I understand it. I mean, we offer really a lot of variety of semiconductors at Infineon. I mean, we offer IGBT, we also offer silicon carbide, and we also offer GaN, not for automotive yet, but more for power supply applications. And we offer, like I said, multiple variety of packages, multiple variety of modules, and all kind of possibilities. So from that point of view, I think we are really offering a very wide portfolio of power semiconductors.
Thank you very much for your answer. And this is the last question for the moment. Thank you very much for your great presentation and for all the answers provided. Dear delegates, in case you have any further questions,
thanks also from my side.
Please address them to the email to Dr. Pai, which you will see now on the screen, and he'll be happy to answer them, I believe. We can move on to the second speaker. Allow me to introduce Mr. Jose Soler Vizan, Technical Director, who is going to speak on the future challenge of rare earth permanent magnet synchronous motors. Hello, Mr. Soler, do you hear me?
Yeah, I can hear you. Good afternoon, everyone. Let me just share my screen. Can you see my screen?
Yes, let me just add it to the... Yes.
Yeah, good. Okay, well, thank you, Valerie. So yeah, the idea of today's topic, basically, we'd like to talk a bit about what we think at Talos is going to be the challenge in permanent magnet motors, specifically the ones with rare earth magnets. So basically, just a brief introduction to Talos. Talos Technology, we're an electrical powertrain engineering service provider. We're based in the UK, and basically we work with our customers, typically tier 1s, OEMs, and major automotive and aerospace manufacturers, to support them in the design and development of electrical machines. Additionally, we actually have some software solutions for powertrain test rigs and system engineering FMEA. Overall, as you may be aware, when you design an electrical powertrain, you do really need to take all the system aspect, even when you are just designing a motor, because it's critical, as this in the previous talk has shown, that you need to really optimize the system, not just single components. So just going to the topic, if we take a look at the current automotive electric vehicle market, very briefly, so we can see three main technologies that are mainly currently in production. On the top left side, we do have providers like Audi and Tesla, which has induction motors on their vehicles. Interestingly enough, Tesla on that Model S, they moved to permanent magnet motors in Tesla Model 3 due to improve efficiency. Then we do have another group of people, mainly Renault and BMW, which are using synchronous wound motor or externally excited synchronous motors. And then the major chunk of companies, car companies, are using permanent magnet synchronous machines on their vehicles. And as you are aware, I mean, the reason for that is permanent magnet synchronous machines, specifically the ones with rare earth magnets, basically neodymium-based magnets, provides the best power density and best efficiency in those motors. Yeah? So today is the technology of choice, and pretty much 85% of the automotive market is currently dominated by permanent magnet machines. If you specifically look, for instance, in the hybrid world as well, the benefit of having permanent magnet machines is that you typically, in a hybrid vehicle, you have very little space available for packaging electrical motor because you still have an engine, you usually have a full transmission. So permanent magnet really is the only option available if you are packaging a motor within the transmission. If we go into electrical vehicle world, in which some manufacturers, they still use legacy platforms, so they're very constrained with the volumes, but some manufacturers, they have already designed electric vehicle platforms with sufficient space to play with the technology, then the variety of options we have on technologies is increased. Now, what happens here is, or one question some of you might have is like, well, okay, why some people go with one technology, permanent magnets, why induction? If permanent magnet machines are the best, why everyone is doing that? Yeah? And the reason comes that already 10 years ago, specifically in 2011, we had a first rare earth crisis. Yeah? In 2011, China limits the export of rare earth material, basically the material that is used to manufacture the magnets, for the permanent magnet motors. And what that meant was that, first of all, the prices of the magnets skyrocketed by a factor of 10. Yeah? Then it was extremely difficult to source those magnets. So you could not manufacture vehicles, and if you were developing new technologies, you couldn't really get hold of the magnets to do any testing. And what that means in terms of cost is that in a typical automotive traction motor, and the cost of the magnets typically was from around 200 pounds, yeah, which is around 250 euros. It did skyrocket to 2,000 pounds, just the magnet. So you can imagine that specific companies, which are more cost sensitive to the markets, 2,000 pounds, 1,800 pounds increase in the cost it can have a hit in the profit margins. Yeah? And it was really a big challenge. So back then, the industry started to mobilize, basically to say, okay, what we can do against this type of prices and so on. However, what usually happens, like the same with petrol, China then stops these constraints, and then the prices dropped significantly. And what that means is then the development of new technologies again stops because it doesn't make sense due to the cost anymore. So what happens is 2011 is that some people, some countries realize the potential of the electric vehicles and the potential of the rare earth into the electrical vehicle world, and they start to find specific raw material sources and start mining. Yeah? So you can see in 2011, most of the mining happened in China, let's say around 90-95%. But since that point onwards, there are a combination of countries, which is US, Australia, Myanmar, Malaysia, and India mainly, that start to as well extract rare earth from their sources. Yeah? However, coming to today's 2022, the extraction and refinement of this rare earth are still dominated by very few players. Yeah? And that's something when you are working on a big multinational, yeah, you're trying to predict what is going to be the cost of your product in the future, you typically like to have a lot of possible suppliers and a very well distributed source, because that will mean you will have a stable supply independently of what happens. Yeah? Unfortunately, today, the rare earth supply market is still very much condensed in very few players, which means, there is potential for instability in the future. Now, this fact, happened in 2011. Today's price of the magnets are relatively stable, similar to the pre-2011 prices. However, we do have another factor coming in, and it's really in 2010 or 11, we were not really manufacturing too many electric vehicles. Yeah? So really, there was not a lot of demand for those magnets. The difference now is that electric vehicles, basically, you are seeing in today's news, pretty much every manufacturer are launching every month new electric vehicles. Yeah? And the predictions are that the sales and manufacturing of electric vehicles are going to follow an exponential curve from this point up to 2030. Yeah? Independently, if you look for more optimistic scenarios, that would be looking to have around sales of our stock of electric vehicles of around 200 million by 2030, or let's say more conservative, 150 million vehicles. What that means is the demand for rare earth materials just for automotive are going to increase dramatically. That, together with the increased use of green energy generation, basically wind turbines, that requires a lot of permanent magnets as well. The consumer electronics, white goods that are as well using permanent magnet machines. All that means is that the demand for these magnets are just going to go through the roof. And some studies are already showing that in the period between 2025 and 2030, we could expect some tensions already in the market. Yeah? The level of tensions is unknown because we don't really know how many vehicles are going to be really manufactured. But there's high probabilities there will be a tension. Together with the tension, that will mean cost. There is another factor, which is the increased awareness on environmental concerns. Yeah? The way currently, maybe mainly in Asia, the way this raw material is extracted, currently they are not using very environmentally friendly processes. Yeah? However, that something can change. Yeah? The processes that are using Australia and the US are much more environmentally friendly. However, in any case, if you are planning to develop a new technology in your company, it's critical you start to think a bit more in the long term. And if you want to protect yourself against potential changes in costs, or dramatic changes in costs, that can completely absorb and destroy your profit margins. So what that means is that, okay, we have our permanent magnet motors, which are great, high power density, high efficiency, very small dimensions, I can package anywhere. However, I'm concerned about these points, which a lot of our customers actually are coming to us because of this. So what can we do? Yeah? So if you take a look at what alternatives we have in terms of technology. So we have on the top left, we have our permanent magnet motors, which can be either surface permanent magnets or internal permanent magnet machines, where we put the magnets inside the rotor. And then we can go for non-permanent magnet solutions. Yeah? Starting from the right side, we could have the wound synchronous machines or externally excited synchronous machines, where we have, instead of magnets in the rotor, what we do have are coils wound around a teeth. Yeah? The stator is very similar to the permanent magnet ones. Then we could have as well induction motors that we have seen, for instance, Tesla used originally, and the Tesla is Audi or e-tron. In this case, well, as you may know, the rotor is made of rotor bars, rotor cage, typically aluminum or copper if you want to get higher efficiency. Or ultimately, we could have switch reluctance machines, which effectively work in the principle of the changing reluctance. And what that means is that the rotor is just made of laminated electrical steel. Yeah? So these type of rotors are very robust because there is no coils, there is no conductors, magnets, or anything like that. However, they typically have relatively high NVH compared with the other technologies. It's true that it has improved significantly over the last years because a lot of investigation has gone into ways to optimize both the motor and the controller of this motor, to minimize the noise. However, today mainly is finding a niche on the commercial sector, the heavy duty, basically trucks, where noise is not such a concern. Another specific characteristics of this type of motors is that they don't use inverters, they need a converter. So basically, the permanent magnet motor, the synchronous motor, and the wound synchronous machine, they can use inverters to feed the current in the stators. So inverters you can find easily in the market. On the case of the switch reluctance, you need a specific power electronics to drive it. You cannot use a standard, what is the standard on the market. So if we take a look a bit on the attributes of these different motors, we can, and we look at the key factors, which will be the system efficiency at one point, the weight and size, what is the maximum speed capability, if it has a wide constant range of power, which, as you know, is very important when you are working in automotive, how robust is the concept, in terms of the rotor assembly, and the NVH characteristics. So if we start with the permanent magnet machine, which will be blue, we typically get a relatively good system efficiency. We can get the best weight and size compared with any other technology. Let's say we have medium speed capability, and this is really down to the fact we have the back EMF. So you spin those motors very fast. You need to be extremely careful with the back EMF generated, and if there is a failure, how you want to manage that. Typically, you can achieve a relatively wide constant range of power if you design that motor in an optimal manner. You can get relatively good robustness on the rotor because you have magnets typically embedded inside the rotor. And the NVH characteristic is quite good. If we look then at the synchronous wound machine or externally excited synchronous machine, we typically we believe, based on our studies, that we can achieve a significantly better system efficiency, because we will talk a bit more in detail. But the benefit of the synchronous wound machine is that because we can control the rotor field and the rotor excitation, we can control the power factor and we can reduce the need of field weakening effectively. And that allows us to improve the efficiency of the system, both of the inverter and the motor at the same time. Then, in terms of weight and size, the synchronous motor, in principle, is slightly heavier than the counterparts of induction motors or switch reluctance motors. However, we believe that, the reason of that is basically you do need a space for the slip rings, to feed the power into the rotor, and you need a slightly more space to put the coils on the rotor. However, the space is a bit relative in terms of the weight, because in a vehicle, the weight of a motor, which is 50 kilos typically, if you compare with the weight of the battery, which can be anything between 500 kilos to 1 ton, is insignificant. So having a slightly heavier or not, heavier or lighter motor, it won't affect significantly the behavior of the vehicle. However, having a better efficiency will have a direct impact on the battery size. So as we have seen before in the previous talk, that it's all related to the battery size, the cost, and the weight. If you can improve the system efficiency on the motor, that means that even though the motor might be slightly heavier, because the efficiency can be made better, effectively you could have a better battery range or vehicle range, or a smaller battery, which then you are saving total weight effectively. Then, if we look at the maximum speed capability on the synchronous wound machine, we'll be talking about a mid-range, because, we do have those coils on the rotor that we need to be careful how to design those. It's just it's a technical solution. It's not that it cannot be done. It's just generally in the industry, there is still not a lot of knowledge spread around the companies about the solutions available. But you can effectively design high-speed rotors with synchronous wound machines that will perfectly operate up to 16,000 RPM. Then the synchronous wound machine has the best constant range capability, because we can control that field, the rotor. And in terms of the robustness, we will be talking about medium capability and robustness, because we have those coils. But again, that doesn't mean it cannot be done. Yeah? It's just in absolute terms, yeah, it's worse, for instance, the switch reluctance, because the switch reluctance construction is very simple. But is durable, yeah, for the automotive world, and the type of speed range up to 16,000 RPM that we typically need to be operating at. And then in terms of MVH, pretty much all the different technologies have similar behavior or can have a similar behavior. You optimize those attributes. However, as previously mentioned, the switch reluctance machine is the one that definitely has a worse performance due to the way it's excited. It's not excited with just typically a sinusoidal current, so it's more a pulsation. Therefore, that pulsation generates specific force profiles that increase that MVH. So if we look at this graph, this radar graph, we can already start to see that the synchronous wall machine actually competes in very close terms to the permanent magnet machine. At Talos, we do believe that is one of the best alternatives to have non-magnet-based technologies in the vehicles. If we look a bit more specific into the synchronous wall machine, we can see we have talked about the fact that we have a wide constant power range capability. We can achieve a good efficiency in all the driving cycles because we can effectively optimize the rotor field excitation together with the stator. It is safe under short circuit, so because we can de-excite completely the rotor, that means if we have a short circuit in the system, the short circuit currents, transients, will be lower than the permanent magnets and the induction motor, so that will limit any potential damage into the electronics. It hasn't got any drag losses, so they're very low because there is no permanent excitation. You typically use a permanent magnet motor, as you know, in a vehicle, and you're running in the highway but without any power in the motor, because you're still spinning the rotor, you're still generating losses inside the rotor. The only way to remove those is actually to have a clutch locally to stop the rotor spinning. This as well is true for the induction motor and the switch reluctance machines. Yeah? There is no excitation, so there is no drag losses. And then one of the key benefits of the synchronous wall machine is the high power factor that can be achieved. Due to the fact we can control the excitation on the field. And what that means is that we can have a smaller inverter. And we have seen on the previous talk that actually the inverter is actually one of the most expensive components in the vehicle. So we can actually reduce the size of the inverter, or the current rating on the inverter, and the current rating on the switches on the inverter. We can actually reduce the cost of the system. Okay? Now, why this type of motor hasn't been invented recently? It has 100 years. But why hasn't been used in automotive before? The reason for that is that there are two main things. One is you need a specific electronics to excite the rotor, yeah? Because you need to be able to inject current in the rotor. You don't only need just an inverter to excite the stator. You need a small set of electronics to excite the rotor. And today, for instance, in the market, if you go out there to big players, like Continental and so on, there isn't any off-the-shelf inverter with rotor excitation included. Yeah? And what that means is that if I'm developing a new vehicle and I don't want to spend money developing new electronics, I'm limited in the options. Yeah, typically you might go for induction of permanent magnet machines because you can have off-the-shelf inverters. However, if you go into high volume, typically you can afford to develop bespoke inverter technology. Yeah. So this challenge is not relevant. And then we expect over time, big players are going to start to realize of the potential as well of this type of motor technology, and they will probably launch this type of power electronics in the market. The other challenge that a lot of companies are facing is the design is more complex. Yeah? Because effectively in the rotor, we don't have just a rotor lamination and a magnet, yeah, they just insert it there and that's it. No, we have a rotor lamination, we have coils, slot insulations, we need to have rotor retention methods and so on. So it's a lot more complex, which the challenge is basically to find expertise in the companies, yeah, to actually design this type of machines in a robust manner. So in any case, the key on this type of technology is that if you optimize together the mechanics, the thermal, the electromagnetics, and the manufacturing, we believe the motor performance that can be achieved is comparable to a permanent magnet synchronous machines. Yeah? So, and that's key, that including with not equivalent cooling, yeah? Because one of the key things is always, if you compare apples with apples in the exact same conditions, 99% of the times permanent magnets will always win. Now, this type of non-magnet-based technologies, in order to make them competitive with permanent magnets, we need to, for instance, improve the cooling approach. Yeah? So typically, we will be looking to improve cooling in this type of synchronous wall machines to be able to extract better the heat out and then get closer to the permanent magnet synchronous machine performance. So if we look a bit closer into the rotor, yeah, which is the key, let's say, challenge when you're designing this type of technologies, we can see, starting from the right, we have the main one, which is the coil retention method. So you have the coils, yeah, but this will start to spin, and the coils will like to just, due to the centrifugal force, will like to come out of that rotor. So typically, we need to design a special way of retaining these coils in position so they don't suffer, basically, and they don't break over time. The brush and the slip ring needs to be optimized as well, so it lasts the lifetime of the vehicle. So this type of motor are designed so that they will last for life. Yeah, they don't need maintenance. Yeah, it's critical as well that the manufacturing process is understood from the beginning. Yeah, because the manufacturing process will as well drive your whole design on how you're going to build these coils. Then it will impose certain constraints. As well, it's very important the rotor assembly stiffness, because now we have a relatively heavy rotor. We need to make sure that the rotor dynamics are correct, you know, in the whole operating range. We need an appropriate cooling strategy for this rotor, yeah, to cool the coils. And as well, we need to investigate the best rotor excitation circuit, you know, to minimize the current needs with the minimum inductance on the rotor and the field and so on. So the key is that, or the key message we want to highlight is that with a good design, externally excited synchronous motor we believe are the best alternative to not have magnets on the vehicle and still have a good power density and drivability on the vehicle. So as a conclusion, basically, I would like to highlight that in general, we expect all motor technologies are going to coexist in the future, yeah, because we have all sorts of applications. We're going to have high premium applications or motor sport applications. So in those cases, we are going to always have permanent magnet-based machines, yeah, because the cost is less relevant, yeah. And the same as, you know, petrol and diesel engines, yeah, they have coexisted because they have different use cases, yeah. Now, based on the current forecast and productions and how the world is changing, we could expect some rare market tensions between the period 2025-2030. And yeah, it's important that you are planning to design this type of, or you're planning to design a new powertrain, that you start to think if you are comfortable, you know, with the potential risk coming in the future. The externally excited synchronous machines are a good alternative to eliminate the rare earth magnets while keeping a good efficiency in the driving cycles. But ultimately, the selection of the optimal topology for this motor really requires a careful consideration of the use case and system integration. Yeah? You always need to look at the system. It's very important, and it's always we talk with our customers. It's like we need to not just look at the motor. I mean, what inverter you're using, the gears. Yeah, we look at different gear sets. You know, 1 speed, 2 speeds. You know, more complex, let's say, topologies of combinations of speeds and multiple motors, because we believe it's there where we can really extract the maximize efficiency and minimize future risks. as well. The performance requirements, we're looking at, imagine extreme motorsport F1 for the turbo that spins at 100,000 RPM. That's always, most of the time you're going to need permanent magnet machines. Yeah? It will always be there as a technology. As well, some reasons of why you might choose one technology or other might be reuse of either motor technology or power electronics. Sometimes, you might have already inverter in your company and you want to reuse it, and you don't want to develop a new one, or vice versa. As well, it's important to understand what is the part costs you're targeting, or what are the investment requirements. Yeah, because if you need to develop a new line, manufacturing line or not, what can be reused if you're moving against different technologies and so on. And ultimately, as a company, there needs to be a strategic thinking and decision to minimize potential future supply chain risks. Yeah, and that's something typically as an engineer you might not consider that, because typically we do like to always improve the power, really minimize the weight. But there are other factors, yeah, geopolitical factors that actually might force you to move in different ways. And we have seen that with Audi and BMW. Yeah, both are premium manufacturers. Yeah, and both they have gone away, at least for the relatively high volume products, from magnets. The claim is mainly due to environmental concerns. However, the potential shortage of magnets as well is in the dance, yeah? And it's a fact. So it's something is happening, yeah, and it's starting to be a move. We're seeing a lot of the customers giving us, asking us the questions, what to do in the future, and it's important if you're looking into new developments that you start to look at these challenges, yeah, you might be facing in the future. Well, thank you very much.
Thank you, Mr. Soler, for your great presentation. We already have quite a few questions that came up for you. And I'm going to start with the first one, which is, what is the max DF/DT allowed for the electrical machines these days? Is it still around 10 kV or higher meanwhile?
I mean, there is not a standard per se. Yeah? It all depends on how you design the insulation. Actually, these days, there is a lot of movement in the magnet wire industry, because the use of silicon carbide basically means you have higher DV/DT. There is not I don't have an exact number, yeah, because it's actually moving away from what used to be the standard. But if you send me an email, yeah, I will be happy to answer you specifically. I don't have the numbers.
So I'd just like to kindly ask the delegate who asked that question to send an email, which I will show a bit later on the screen. And feel free to send an email and you will receive a more detailed explanation. Thank you very much for your answer. And moving on to the next question. Is the efficiency of EESM in your spider chart based on any specific cycle? EESM advantage is mainly at higher speeds, but has disadvantage at lower speeds.
The efficiency is based on let's say a standard driving cycle. Yeah. But as we have seen before, depending on what cycle you are targeting, in NDC, WLTP, Artemis, or fixed operating speed, the efficiency changes. Yeah. The benefit of the synchronous wall machine is you get a good efficiency on the mid-range speed, actually, similarly to the PMSM machine. It's true that if you compare the efficiency at lower speed range compared to PMSM, it's worse, yeah, because on the permanent magnet machine, you don't have excitation on the rotor, so you don't have those losses. Yeah.
Thank you for your answer. The next question is, if EESM will take more market share, may we expect that the price of copper will go up due to demand versus supply economics?
Well, I mean, the price of copper, the amount of copper in the rotor, I mean, there is a bit of copper, yeah, but it's not the only driver. The copper prices, to be honest, are going up and down continuously. Of course, if suddenly there is more demand, it will go up. but still the cost of the per weight of copper is not the same as the cost per weight of the neodymium magnet-based magnets. Yeah? It will need to go up significantly to suddenly lose that benefit. Then potentially, one of the benefits of the copper is you can do recycling, yeah? Which currently neodymium-based magnets are not so easy to be done. And potentially you could even move to aluminium in the future once there is more wires of these types available in the market.
Thank you very much. Moving on to the next question, which is, do you have any idea about the lifetime of the brushes and the friction losses?
I mean, the friction losses really depends case by case, yeah? There is not a single case, because if you are designing a motor that operates at 1,000 RPM, it's not the same that it's operating at 20,000 RPM. In terms of the lifetime, what I can tell you, you can design brushes that last the life of the vehicle, yeah? Typically 10 years, 15 years. So if you look at Renault or BMW, there is no specific requirement to do a change in brushes, yeah, during the lifetime of the vehicle. So they are designed for the lifetime of the vehicle.
Thank you. Moving on to the next one. This ESM needs external supply and its control circuit to exit the rotor. How this affects the overall efficiency of the system?
That's considered when we have done this comparison. We consider the losses, yeah, effectively, and the excitation on the rotor is very small. You know, we're talking about I don't know, 20 amps of current required or less. So the amount of losses on that excited are extremely low. Yeah? So they are, let's say, non-relevant compared to the losses of the system.
Thank you very much. The next question, we have quite a few of them, is which technology would suit best a large air gap application?
Well, that's very, it's too open question. It's difficult to know, really. The question is why you have that large air gap application. Typically in automotive, you know, we're talking between 0.5 to maximum 1 millimeters. And that's not really a large air gap from my point of view. So it's difficult. Again, if you can clarify this question, maybe answer it afterwards. Yeah.
Thank you very much. And the next question is, have you evaluated Michelson-Wundt field magnet free wireless excited rotor technology?
We have looked at it. I mean, there are the Mahle proposal is not the only one. At the end of the day, rotary transformers, yeah, or sort of rotary transformers have been there for a very long time. Now, yeah, they do claim there is no need of maintenance, yeah. But the reality, if a brush is designed correctly, you don't expect to have any maintenance need, yeah, on the brush. So to be honest, it will all come down to costs, yeah. How much cheaper can be that wireless solution be compared to the brush system, and maybe in specific cases in which you have a lot of vibration levels, maybe having a wireless excitation actually have an advantage, yeah, compared to a brush solution.
Thank you. The next question is a bit longer, so I'll display it in two parts. And it is as follows. The ESM, there are copper losses in the rotor, which should make it a lower efficiency, especially at low to medium speed. Why does your comparison of the attributes give it such a high rating compared to the PMCM?
Yeah, because as I said, it depends on where you're operating at. Yeah? One of the key things is the synchronous one machine, you can control the field, yeah, generated on the rotor. And what that means is that compared to permanent magnets, in which the field is fixed, on the permanent magnets, you need to do field weakening, yeah, to operate in certain areas. And that has an impact, significant impact actually in the efficiency. So that's where the benefit comes on the synchronous one, is that you don't need field weakening, or you need less field weakening, and that the power factor can be higher. So the losses on the inverter are lower. So that's the reason why we're talking about system efficiency, not just motor efficiency.
Thank you. And the last question for the moment is there a way to have ESM without slip rings? Would it be better than a typical induction motor?
Well, actually, we just have a question about that. You can have wireless, or solutions, Imagine like a rotary transformer, effectively going into the rotor. So there are those. There is nothing like that on the market today, because depending on how you are designing that, you need then a specific electronics as well, and so on. So, but yeah, there are technological, let's say, solutions, to have non-brush-based power transfer on the rotor.
Thank you. This was the last question for the moment. Thank you very much for your great presentation. I'm looking forward to seeing the panel discussion. And for now, I will display your email on the screen. So, dear delegates, please feel free to contact on his email, which you can see on the screen. Thank you once again, and see you very soon on the panel discussion.
Thank you. Thank you very much. Thank you, everyone. Have a nice day.
So, dear delegates, it's time to refresh a bit, to have a small coffee, tea break, approximately 10 minutes long, and see you very soon. Dear delegates, welcome back. I hope you got the chance to refresh so we can move on to session 5, thermal management for e-motors powertrains. Allow me to introduce our third speaker, Mr. Florian Rochte, who is strategy consultant, and he's going to present on software-defined vehicles, the third generation of cars. Hello, Mr. Rochte, do you hear me?
Yes, I can hear you well. Can you hear me?
Yes, I can hear you very well.
Wonderful.
In your own time, feel free to share your screen, and I will leave the stage to you.
All right.
I see your presentation.
Excellent. All right. Thanks, Valerie. Thank you very much for having me here. I'm a late addition to the agenda, so I'm not really talking about thermal management of e-motors. I'm actually talking about our software-defined vehicle, and I will use Tesla as a case study. And I hope this will be as entertaining for everybody involved as it gets. It will not be as technical detailed as my predecessors' talks. But first, allow me to introduce myself. So I started my automotive career many years ago at a company named Bosch in Stuttgart. And I started a professional career at a company some of you might remember is called Siemens Video, Frankfurt, Germany, as a system test engineer for electric power steering systems. We're building highly safety critical systems very early in the game on the market back in the day for Volkswagen and Audi. This company then eventually got bought and integrated by Continental, where we continued to work on the same topic. I worked over 7 years there as a group leader for system development. And in 2012, I moved over to a startup called Tesla Motors back in the day. I was the first member and the founder of a team for vehicle software validation. We just sold a few hundred Model S cars, and I started to build up that team, and I will give you a little bit of an insight what we did there during this presentation. 2018 to 2019, I worked as a director of integration and validation for smart components at NIO. And starting 2019, I started becoming a freelancing consultant and advisor for all the topics I will show you in the next slides under the roof of iProcess Consulting LLC. Right. So first, a little bit of a history. So the car, as the modern car, was basically invented over 130 years ago. And for a long time, it was the same thing. It changed its design and the looks of it, but it was a mechanical product for almost 100 years. All the parts of the component of the car, all the components of the car were controlled by mechanical connections, and the car was built like that until the 1980s. So in the 1980s, the EE generation of cars started, and the companies started to develop and implement electronics and electrical components, starting first with the upper class generation, the upper class of the vehicle in the first generation, and then starting over time, technology got more affordable and got integrated also into middle class, and in latest in what we consider called the affordable class of vehicles. This was, as I mentioned, starting somewhere in the 80s, and it basically is the style of cars, the second generation of cars as we know it today, and as most of us have the car like that in the driveway in their garages. So starting now, we are moving over to what I call the third generations of cars. So the cars are no longer an EE product on a mechanical platform, but they are fully integrated products, and they are defined by the software that is running on them. And it is important to mention this is not a connection or collection of components, but what we'll see here is an integrated, complete product that is actually providing a mobility experience to the driver or passenger, and is communicating with the environment, and is it may be driving by itself. It might be provide other features or entertainment to the passengers. And it is all under one collective understanding of a software-defined vehicle. So in short, this is the third generation of a car. So why are you doing that? So what's the motivation for that? Why are we doing that? So first, you have a continuous improvement of the user experience. The user buys a vehicle, a product, and has a continuous improvement and feels that the product stays fresh, similar to what you see with iPhones or Android phones. Your vehicle is getting new features and it's getting better over time. This can be something you didn't have so far, but it can also be an improvement of what you have so far in your vehicle. So this gives us a very new option to talk to our customer and the buyer of the car, because now you suddenly have an interaction with the buyer after the initial sale. Originally, the car was sold to a buyer, and the buyer left the dealership and basically only came back to change the oil and buy new tires. But there was no direct interaction with the OEMs anymore. So this is changing now, and this is generating new revenue streams. So I can basically take a feature the customer didn't know about or didn't want or didn't have the funds to afford it, and can sell this feature to the buyer later. So when he maybe gets a raise or a bonus, or figures out that he forgot to buy an original feature like a streaming service, and they can order that feature separately and integrate it in the very same car. So this also generates, I go back once. This also generates a new opportunity for used car buyers, because right now you don't have to buy the exact car you want, but you buy the car that comes close to it, and then you can actually ask for modifications. You can pay for those modifications, and you can actually have the vehicle exactly as you want it, even though it is not, at the time you buy that vehicle, it is not urgently equipped with those features. It provides a new feedback loop, and this is a very important thing. So the cars can now talk back to the OEMs, to the developers. So far, developers are coming out with a feature and with a car design in the best guess and hope that this is what the customers want. But there is no direct feedback loop at scale that explains that back to the developers and makes their decision-making process easier. The same thing on the design of the hardware, for example. You have to design the hardware assuming some sort of worst case usage. But we had situations, especially at Tesla, where we actually later looked at the feedback loop and realized that the hardware is used in a totally different way. And in some cases, it was used way less than we assumed it would be. So there is an opportunity for cost reductions or for improvements in the vehicle hardware and mechanics, also through that software reported feedback loop. You have something which is called preventive maintenance. So instead of having a customer breaking down at the side of the road because there might be a problem with the, let's say, the 12-volt battery of the car, or they cannot start the car in the morning when they have to go to work to an urgent meeting, you can tell them a week ahead or two that they should plan on the maintenance of their, in this example, 12-volt battery, and they can avoid that. The cost of a car that is actually breaking down during use or during travel is a large amount higher than the cost of a preventive maintenance, where you can actually provide a solution to a problem before it occurs. You can avoid physical recalls. You probably heard or read about that in the news today. I read about it in the news today. Tesla is going to do a recall for the window lift, and that window lift will be updated over the air. So you still have to file for a recall, but instead of having this bad experience for a customer to bring the car back, have to stay at the service, or have to leave the car there and take a rental car or anything like that, you can do actually the recall over the air into the vehicles while the cars are parked overnight in the people's garages. All right. Here are a couple of numbers to get you a little bit of an understanding what we did there. Those numbers probably reflect time frame around 2015-16. So we got about 700 engineers, technicians, and interns working on the Tesla software team. And we did 150 customer software releases per year. That's not a typo. That's 3 per week in average. Of course, not every customer is getting 3 software updates per week. That would be undesirable by the customer and by the car manufacturer. But they're very targeted sometimes. Sometimes the software update only goes into the market of Hong Kong, or sometimes it only goes to the factory. Sometimes it's only going to cars that have a certain feature or build pedigree. So overall, the development provided 150 signed software releases, fully tested. So this came out of our continuous integration system, and the CI system produced over 20 software builds per day going into the entire car. And the number of tests we ran on the full vehicle, full regression test, was over 17. This number is just the 3 releases plus 1 per day. 2 per day. So what's needed to do all this magic? So this is a word cloud. You see a lot of different things. You probably heard about a lot of different of those things. So I will pick a few of those and talk about those into in detail in the upcoming slides. So I'll grab a quick zip so you can read. All right. So first, Agile in automotive. A lot of people are talking about Agile in automotive. I haven't seen a lot of really good implementations. I have seen a lot of people working on the implementation. So first, Agile in automotive, in a summary, in a way I saw it working. So you run a ticket-based implementation system. You're basically not allowing any work to go into your entire work flow without a ticket tracking the efforts, tracking the activities around that. To a point that at Tesla, we actually even had tickets to change the tires on the test cars. You have a synchronized sprints. That idea is not new. It's out in computing and software development since 1988, but it currently just makes it over into the automotive industry. So you have a lot of different developers working, but they are synchronized in their delivery and integration. That leads to the release train approach. So you basically, you develop your feature, you make it into the train that leaves the station every other week, for example. And if you don't make it into that train, you will have to wait for the next train going out 2 weeks later. Of course, there's always an urgent release coming out. Everybody who's involved in software knows that this happens all the time. So you get a special urgent release train. That urgent release train can happen in between the actual scheduled release trains. You have a hard control through a change control board so that there is no freedom of the developers to decide where to put their changes and where to put their development outcome. It will be decided through a change control board. And I have a slide to explain who is on there. And everything has to be approval permission based on a branch of software status. Same group usually that runs the change control board is also a part of the long-term planning committee. So not everything is happening in 2 weeks. I really want to underline that. Even at Tesla, it doesn't. So some stuff, some developments take many months or even years. So they're done in a long-term planning committee. The release trains are actually scheduled for 2 weeks of integration period. And here's the very, very important thing, working in product increments. So every build out of those 20 software builds that is generated by the CI system is actually functioning. So every build can be used, put it on a car, and you can drive that car with all the functionality. Maybe some of the new functionality is not working yet, but the vehicle has a software backbone that is always, at any time, is capable of running the entire system. All right, so how does the toolchain actually look like for that? So you have somebody providing an input. That input can actually come from a variety of sources. One of them, product engineering. Product engineering is the team that tries to guess what the customer wants tomorrow. Coming back from service engineering, that's the team that figures out what the problems are today. It can come from the factory. They, after all, have to build the car, and they might need some modifications in the development of the product. It can come from marketing. Marketing usually comes up with the great promises, and they actually we have to fulfill on the engineering side, fulfill the marketing promises. It can come from regulatory. That can be either a recall, as we just talked about, or it can also come from a change in homologation requirements. one interesting thing, it can come from engineering itself. So if an engineer has a great idea, they can also provide that as an input into the whole agile process, and it will be discussed and decided on. Advanced development, as everybody is aware of, these are the guys who are working on the technology of tomorrow. The customer itself can actually provide an input towards the development team as well, which is, I believe it's a very, very powerful tool to actually not only try to guess what the customer wants, but to ask them if they really want that. And then that's a Tesla specialty. There's a lot of involvement of the CEO as well. So whenever anybody from this group is providing an input for the toolchain, it actually goes into a Jira ticket. It doesn't have to be Jira, but was the tool of choice. And it goes into a committee. And in this committee, I explain in a second who is member of that. If the committee decides to implement a certain change, it will go to the developer, here illustrated as the working hero at the desk. And then from there, it goes through a interface. It goes into a repository, into a software repository. And then you have a CI system. And the CI system is doing a lot of things next to compiling the software. It also runs a lot of tests. And it actually provides that then into the cloud. That is the point where if we would talk CD, so continuous deployment, I would count that as a CD, but it does not continuously deploy out of the cloud into the customer car. So who is part of the organization that is actually run the whole decision making? So instead of having a hierarchy, a large hierarchy where you have to go step by step up, and it takes a lot of time, this concept here is actually for fast decision making and for a fast development. So I moved that here. I'm not sure if you guys see that piece at the bottom, but now you can read everything. So who's member of that organization, of this committee? So it's the project manager responsible for the sprint, the VP or director or whoever is responsible for the entire organization. And then the managers of all the different teams involved into the delivery of a release. And then on the right side, important, you have the system integration and system validation crew. So those guys who actually have to put all the work products together and then try to hammer on them to see and prove their reliability in the real world. So this group is responsible for the planning efforts, but it's also the gatekeeper for the change control and also running the planning for the long term. This is not the group that actually does the work. This is the group that actually organizes the work. Next slide. Important. This is the group that has full decision power. Even though this group is not complete sometimes, so we had the situation where the VP was not available due to business trips or similar, and we still had the opportunity to be a full decision-making group and committee. So like this, we are not slowing down the whole delivery just because one member is actually not available at that time. So next slide shows you who actually does the work in the agile organization. So you still have a project manager who's actually helping out with that, but basically the same teams are delegating a member that is actually doing the real work towards the team, and they organize in Scrum sessions. So they basically stand-up meetings, depending on the schedule. That can be bi-weekly all the way up to twice a day. And they're running through the integration effort. They're responsible for the timeline and also for the technical implementation. The head and the organizer of this group is actually the integration engineer on the top right. That's the person who is responsible for the specification all the way to the implementation in the car. All right, moving over to the other side of the V-cycle, talking about automated regression testing real quick. So the goals of automated testing is, so first, CI does not make any sense if you don't have CV or continuous validation. I'm not talking about CD, as I mentioned earlier, but if you produce 100 software builds per week and you can only test one every 6 weeks, the system is not efficient. If you bring up your testing capabilities that you can run a full test in 24 hours, but your development team only produces a new software every 4 weeks, that doesn't work or doesn't make sense either. So it has to be applied where it's useful, and it has to be applied to scale on both sides of the V-cycle. The statement is very simple: test early, fail early, fix early. So in the classic waterfall approach, you are testing something several weeks after it was actually implemented. And in that case, you might, in worst case, some developer creates a bug in the software in the very first day, and the tester finds it at the very last day. So you have the maximum time between creation and problem discovered. And then like that, you run into schedule issues. So test early and fail early and fix early. So the main source of issues in complex mechatronic systems and products is the integration. Most of the time, the component teams are doing a pretty good job developing their own product and testing it. But once you put them all together, you create integration problems. And that is the reason why I state run vehicle tests or system tests as early as often as possible, so that you run integration tests all the way at the very early stage. That doesn't mean that your system works. Some of the features might not be available or working yet, but you will see if they actually create a regression on the different end of your system. Also, what I vote for is allow feature branches, so early development in full vehicle tests. Again, doesn't mean that the system works well, but it will look at the integration of the components. And then here's another powerful thing. It's like combine all levels of testing into one complete picture. What I saw before is that you have people running software tests in a simulation, then on a board, then you have system integration tests, you have vehicle tests, but those don't talk to each other. And everybody has an 80% test coverage and is hoping that the other 20% are covered by somebody else, but there is no direct proof for that. So when you look into automated regression testing, so what you see here, those 4 boxes of testing are actually independent if you run it automated or manually or partly automated. You always have to prepare, execute, evaluate, and report your test execution. When most people talk about automated testing, they are talking about the second box here, the execution. So they do all the steps in the prepare box. So they get a trigger, which is usually a person telling another person to do something. They go and fetch the artifacts, they schedule some time, they book a test bench, they update the test, the DOT, the device under test, they configure it, and then they start their LabVIEW script or the Python script, and it runs through a sequence of tests. And afterwards, they sit there and look at the results and make a go or no, a pass or fail decision and report that in some way. I say a real end-to-end automated testing system has to start from the very first step trigger and end with the very last step, visualization, without any human involvement. That includes the booking of the resources, the configuring of it, the updating, and running the tests and looking at the results. Okay, so one very important thing to make the whole software-defined vehicle work is that the vehicle is actually knows its component and the status of its components. So I just listed up a few here as an example. This is not complete, but so the fact that a Tesla car actually knows what kind of hardware and software is in each of those components, and it has that centrally stored, gives it the power to actually interact with all those components and interact with the server in a way different manner, rather than where you have a lot of different islands in the vehicle. So in this case, the vehicle gateway of the car knows exactly what kind of software and hardware is implemented in the car, and it can actually act accordingly. And as an example, I found those screenshots here online. So you see on the left side, this is actually a screenshot out of an actual Tesla Model S, a fairly old one. But it knows exactly what kind of hardware is in there. And on a different screen, you would see exactly what kind of software is in there. The same thing is the information that hands it over to the service on the right side. That's a screenshot for a service tool. So you can see exactly what kind of hardware and software is in there and what kind of status is in there. So that gives it the power to actually run the software updates and the whole complete feedback loop, really specific to this one vehicle. So I'm talking about over-the-air software updates, or go over this real quick. So one thing is, based on all this configuration that the car knows exactly what's in there, you don't have to package something and send it to the car just for this vehicle. You can let the vehicle decide what it needs. So you can package it up in a universal fashion, and the vehicle can actually pick the components out of such a package. And that makes it much easier for the validation, because the validation has only one package and not a few thousand for each different vehicle configuration on the market. There's a hardware diversity layer. This is a cybersecurity topic. So as soon as you connect a car to the cloud and to other cars, you create a lot of cybersecurity risk. And the hardware diversity layer in this particular architecture actually prevents the modem from being connected to anything that is in the embedded systems that can actually create a harm. In that context as well, there's signed packages. So the software can only be sent by the original server. You cannot catch it and modify it and then play it back into your systems to change the behavior of the system. Same thing as a cybersecurity measure. The same as the production fuse. So as soon as a car rolls off the line, it will get a so-called production fuse burned, and it will refuse all packages that don't have the specific signature. The gateway manifest basically replaces what I just showed you on the slides before. So the car actually knows exactly what's in the car, at what status it is, and at what version it is. And it actually correlates that with the server when it communicates about software updates. So the server knows at any time how many cars with what version of hardware and software are out there in the world. And based on that, you can make project management decisions fairly easily. You get a hardware IDs, as I just showed there in the screen before, and you have the hosted server cloud that is actually spread depending on the markets all over the world. And then you get a communication of the car both over Wi-Fi or you got a wireless cell phone connection. And this is the last point on the slide, the release notes. That's a very, very important thing. Since the car knows exactly what's in there, so if I don't pay for cruise control, the car doesn't have to show me cruise control in my release notes or in my owner's manual. It's not a large book that says with a 3 asterisks, if equipped or paid for in your car. It will just pick out the components that are actually equipped and paid for, and it will show me the exact information to the car I'm driving. And then the binary diff we were using is basically to reduce the size of the software about factor 10 to 100, depending on the software updates. So not to shovel gigabytes over the internet connection every time they're running a software update, but actually bring that down to tens of megabytes. All right, I overshot by a few minutes. I hope that's okay. I'm showing you my last slide here. That's actually the Starman and the car that got shot out by SpaceX to the moon or to the Mars or wherever it is by now. And then on the top right, it's that very same car in my driveway while I was still working at Tesla. All right. I know, a lot of information in a short time, but I hope you had some entertainment with it.
Thank you, Mr. Rogde, for your great presentation. We already have questions coming up for you. And the first one is, do you think there will still be a 4th generation of cars in the future, or will our lives be lived in virtual reality by then?
That's not a question for an engineer. This is a question for like somebody with a glass bowl. But in general, it's probably true that there will be a vehicle generation coming at some point in the future that will not urgently drive on the wheels. But it might look some sort of like a flying car, but it can also be something different. The future is not defined there yet. I mean, it's the same with the 3rd generation. Nobody saw that. There were some visionaries at one point, but we'll wait. So you see that in the time between the generation changes is getting smaller, right? So we had 100 years, then we had 40 years. By that logic, the next change should be as soon as in 10 to 15 years. I'm looking forward to it, whatever the guys are coming up with. I don't have a glass ball. I'm a passenger.
Thank you for your answer. Moving on to the next question, which is kind of a longer one. That's why I'll display it into slides. So it begins. The trend of having all the hardware in the car, but only unlocking the features on a subscription base, it's criticized for not being sustainable.
Yeah,
many cars carry the hardware without even ever using it. What is your stance on this?
Yes, so this is an interesting topic we discuss a lot. So this at Tesla, we were able to do that because we approached the market from the premium segment. And the statistics we saw is then that, I don't know the exact number, but it's a very high percentage is picking the features sooner or later, either right when they buy the car or later. Of course, it is not sustainable to put it into what is called affordable car class yet, but we also see the power of computing, according to Moore's law, doubling every year, and the price of electronics, I'm my co-speakers know much better about that, but it's also going down significantly every year. So I think it becomes more sustainable once the electronics are getting produced in higher numbers and are getting more affordable. But we also see the trend to zonal architectures, and with that, you suddenly have a large, powerful computing system in a car, like what you have with your laptop, and you can add more features to that or not, but it will not change the actual price of the hardware.
Thank you for your answer. And moving on to the last question for now, which I will also display in 2 times. Another criticized aspect is the fact that the end user somewhat stops owning the car, not being able to modify the system in any way and allowing the manufacturer to cripple the car at his will. Any comment on this?
Yeah, I think it is a change also in what the customers want and what the customers will want in the future. I love to use the analogy of people in 2010 who are very sure that they don't want to change their flip phone and they only want to charge their phone every 7 days, and they never use an internet worthy phone in their pockets. And now we are 10, 12 years later, and nobody has any of those phones anymore. For automotive, this will change slower because the product is more expensive. But you already see that when you look at infotainment systems. If you bought a car in the 80s, you could just take out the radio and put your CD changer in it if you want. You can't do that anymore for over 15 years now. So no cars allow you to do that anymore. So is a change we are seeing in the entire industry moving over is both how we build cars, but also how the consumer consumes and wants cars. It's a little bit slower than with mobile phones, but some of the guys out there have to be careful because Nokia was very sure that they will be the market leader in 2022, and they're not. So we will see that changing, and the customers change as well, just a little slower.
Thank you so much for your answers. This was the last question for the moment. I will display your email right now on the screen. So please, dear delegates, if you have any questions you'd like to address directly, please feel free to contact him on his email, which you can see right now on the screen. So, Mr. Rode, thank you so much once again for your great presentation. I'm looking forward to seeing you once again in the panel discussion shortly.
Yep. I see you there.
So see you soon. Thank you.
Thank you.
So, dear delegates, we can move on to our last but not least speaker. Allow me to introduce Mr. Srinivas Malampalli. Hello, Mr. Srinivas. Do you hear me?
Yes, I can hear you. Thank you. Yeah.
How are you today?
I'm doing good. Thank you. How are you?
Perfectly fine. Looking forward to your presentation. In your own time, feel free to share your screen.
Sure. Thank you. I'm just going to share my screen.
I can see it.
Great. Just going to go full screen.
Perfect.
All right. Great. So, hi, my name is Srinivas. I'm currently working with Eaton Research Labs in India. I've been with Eaton Research Labs only for a few months, and again, like my colleague in the previous session, this was a later addition to the agenda. So my topic, as you would have seen, is not related to the thermal performance of machines, but I'm going to talk about the work that I did with Valeo and the University of Sheffield, where I investigated, going with the magnet-free theme, how to use induction machines for hybrid vehicle applications, specifically for emerging markets where the electric charging infrastructure is not available, but the country distances are big, like a country like India, for example, where the nearest next big city is some 600 kilometers away. So hybrid vehicle take-up is going to be much more important and much more feasible than full electric vehicles. So in that vein, I'll talk about induction machines and a specific class of induction machines called pole changing machines. So if I go to the next slide. So the motivation is, as I mentioned before, over this range of electrification of a car, On one end of the spectrum is what is called as a P4 architecture, where you have the entire traction power being provided by the electrical machines. And on the other end is, of course, the IC engine providing the full traction power. And then in between, we have several ranges of electrification. And what we're looking at here is a starter generator application, where the what is called a P0 or a P1 architecture, where the machine is placed in addition to the IC engine. And the idea is that the machine will be able to not only crank the engine, but also provide energy to charge the battery, as well as to provide some amount of boost torque during high-speed operation, for example, during cruising on the highways. Now, induction machines have very good peak torque capability because theoretically you can never really run out of torque as long as you have enough current to push into the machine. But it is quite well known that the losses of an induction machine are quite a bit higher due to the current flowing in the rotor, which is absent in a permanent magnet machine. Though for high-speed highway cruising, induction machines are quite attractive in terms of efficiency, because you don't need much demagnetizing current, or you don't need demagnetizing current to enable operation at high speeds during cruise control. And also not to say the cost is quite a bit lower. And in markets, emerging markets in developing countries, cost is a key driver of customer uptake of these kind of hybrid electric vehicles. So having laid down the motivation, go to the next slide. So the objective of the exercise was to see that if we try to build an induction machine which has the peak torque required to crank the engine, but also can operate at wide operating speed ranges, which also requires a higher torque or enough torque at high speed, you could see that looking at the torque speed curve of an induction machine, you would end up having to increase the peak torque at the base operating speed, so that as the torque drops off at higher speed, you still have enough torque. Or the other way is to increase the corner speed, so that when you push the corner speed further higher, you still have enough torque as the torque decreases as a hyperbolic function. Both of these have a disadvantage because both of them result in either increasing the size of the machine because you need more torque at the base speed, or increasing the amount of current that your inverter can provide, thus increasing the cost and the size of the inverter. And this is where pole changing machines have become quite interesting, because you could use a higher pole number when you're operating at low speeds or during cranking operations, and that results in having a high torque. But as you're approaching higher speeds, you could reduce the number of poles and then take advantage and leverage the wide speed operating performance of the 4-pole machine. And these machines are not new. As such, pole changing winding machines are probably close to 80 years old. But with the advent of electronics, you can overcome several challenges of classical pole changing machines, where one half of the windings of the machines which belong to one pole number are not being used, so you lose a lot of power density. So that can be overcome, and Professor Thomas Lippo had proposed, and his student had proposed, how to use the electronics to change the number of poles of the machine. And very briefly, how this is done, and this is a state of art, is that you have to split the windings of each phase into 2 coils, like is shown here. A phase is split into A1 and A2. B phase is split into B1 and B2, and so on. And this allows you to switch the direction of current in one half of the coils, as is shown here. So what was previously a north-south 4-pole machine, by reversing the current in one half of the coil, allows you to have a north and a south pole, thus making it a 2-pole machine. And this can be seen that by adding the MMFs or subtracting the MMF, you will end up with a 4-pole or 2-pole air gap MMF. And being an induction machine, the rotor can pick up any of these 2-pole numbers. The disadvantage of this machine, which was proposed then, is that once you switch from a higher pole number to a lower pole number, you actually lose a significant amount of torque, not only because of the reduced pole number, but you also lose the torque in the high-speed region because of poor winding factor. So while the machine that was proposed there might have been okay for operations with pumps or say blowers, it's not particularly suitable due to this poor winding factor when you change the pole number by half to half. So, and another effect of this poor winding factor, of course, is well known, that you end up having to push in more current, which results in poor efficiency. So to overcome this, and what is shown here is this is the current state of art, a three-phase pole changing winding machine. An interesting way to overcome this is to use a six-phase pole changing winding machine, and that surprisingly solves a lot of the problems when it comes to winding factor. By having a four-pole winding, which has only a 60-degree coil span, what you end, or a phase belt as it's called, when you have the current reversed, you will see that for a 60 degrees phase belt winding, the winding factor does not degrade with the influence of pole changing. That's the advantage. So you end up with similar copper losses. And also, because you have a six-phase machine, six-phase induction machine, you can now start to inject third harmonic currents when you have a lower pole number and extract even more torque out. There is a disadvantage that more inverter switches are needed because you're now splitting a three-phase machine essentially into a six-phase machine. But it's important to remember that the cost of an inverter is based on the current rating of the devices. So we're not increasing the overall DC bus current, but we're rather splitting these currents into lower current rating devices. And this works out in our favor, actually, if you're going for volume production, because we can get several number of lower current rated devices, which ends up to be economically quite beneficial, especially for low voltage systems where the current per phase are quite high and you require to split your inverter switches into a smaller number. So the why a six-phase pole changing, as I explained previously, you have the benefit of having a better power winding factor when you switch from 4 poles to 2 poles, for example, or 8 poles to 4 poles. And this would be the kind of winding arrangement and inverter connection. And when you connect the neutral points of the 2 3-phase sets, you can actually inject third harmonics, because what you end up with is what is called a 6-phase asymmetric induction machine, which allows you to inject third harmonic. And as you can see here, you actually are able to get a third harmonic MMF in the rotating magnetic field, which allows you to extract up to 15% more torque as a result of third harmonic injection if the application requires it. So with this theory established, we went ahead and built a prototype induction machine with some of the details shown here. Again, this was a smaller scale machine to fit the dyno requirements, but the idea was to demonstrate the concept using a smaller or a lower rated 3 kilowatt induction machine that was prototyped. And the windings were brought out so that externally we could make the connections that were shown in the previous chart. So with one machine, 4 different topologies are possible. And the first topology is a standard 3-phase machine with a 60-degree phase belt. And the second and third machines are essentially the state-of-the-art machine with a 120-degree phase belt with 4-pole and 2-pole connections. And the last 2 machines, or the last 2 connections which result in the last 2 machines, correspond to the proposed 6-phase 60-degree phase belt connection, which gives us the advantage of third harmonic injection as well as higher winding factors at the lower pole number. A D-space controller was used and a 6-phase inverter was developed, and I will just have some more details on the inverter in the next slide. So the inverter was essentially 2 Infineon hybrid pack 2s inverters, which are quite popular in the automotive industry. And these are connected in a fashion that is shown here, where the individual phase windings and the coils are brought out. The model is built using MATLAB Simulink in DSpace, and then that code is then ported into the microcontroller in DSpace, and a PI controller is used to put the machine through its paces and establish put the machine through its paces, and also to establish the torque speed characteristics to determine the performance of this machine. Right. So the test methodology was quite straightforward and quite well known. To achieve a different torque at different speeds. At every speed, the Q-axis current of the machine was varied, and the optimum point or the peak torque point for a given Q-axis current was determined. And that was used at every operating speed to plot the torque speed characteristics of the machine. I will not go through each details of the chart, but just the takeaway from this is that we get a good correlation for the baseline case, and this measured and simulated test data is repeated for all the 6 different machines connections that I had shown previously. And similar tests were performed for all these machine configurations. And what is shown here is just the envelope of the torque speed characteristics, but to get the efficiency plots, this test has to be repeated for each operating torque point. And as you can imagine, that is a lot of tests and graphs, and I thought it not wise to include it on this in this presentation. But I have the efficiency plots and the torque speed maps in the subsequent slides. So this slide shows the comparison. So what we are interested in is this 20% improvement in torque over the state-of-the-art pole changing machine, and also this extended wide speed operating region, and which is much more clearly demonstrated in the extended power operation that we get in the flux weakening region. And this is of interest because in the flux weakening region with a hybrid vehicle, there is no torque boost required, but the area under this power speed curve essentially shows you the extra energy that can be extracted from this machine to charge the battery. So that is kind of going to add to the overall energy efficiency of the vehicle, because you have now additional energy that can be extracted during the cruising, which would not have been possible if a similar sized inverter and induction machine was used in place of this pole changing winding machine. The state-of-the-art machine is now compared with a baseline induction machine. As expected, the peak torque is lower and the efficiency is also lower, but the extended flux field weakening region is still possible with a state-of-the-art pole changing winding machine. But when we look at the graphs for the proposed machine, now we see that we can get higher torques like the baseline machine. We are still able to take an advantage of the extended flux weakening region, and we will get about 3% higher efficiency than the baseline machine in the flux weakening region due to the slightly reduced iron losses. We have to remember that we have reduced the pole number, so we can reduce the operating frequency at higher speeds, and that gives us a benefit of not only extended torque flux weakening regions, but also higher efficiencies in these flux weakening regions. What is shown here in the power speed characteristics is this area in the pole changing winding machine, over which you can extract a bit more energy to charge the battery. And that is what the dotted region represents. It's essentially the extended power capability due to pole changing winding, as well as the higher peak torque that you can achieve compared to that of the baseline machine. And the energy efficiency or the efficiency of the machine is more apparent when operating above the base speed of the pole changing machine's operation. So essentially in this case, we are going from 4-pole to 2-pole. So the efficiency when we are operating above the base speed of the 2-pole machine is much more apparent. So essentially you have a higher, darker colored region here, which is representative of higher efficiency. Of course, controls is the other big work, and there's a lot of investigation to be done. And just to show you kind of a disadvantage if you did not have proper field-oriented control, what I have here are the speed versus time when I change the number of poles and also change the torque on the machine with no field-oriented control. And as you can imagine, there is a 2-pole and a 4-pole magnetic field existing in the rotor at the same time, and this results in large oscillations in the speed if you're working in open loop. Once you close the loop using field-oriented control, then you can begin to see that these harmonics or the ripples due to these changeover from 4-pole to 2-pole are well controlled. And it's quite interesting to see the 4-pole and the 2-pole d-axis currents actually kind of decreasing down to 0 from 4-pole to 2-pole, and the 2-pole d-axis current going from 0 to the set point value, and the similar variations for the q-axis current, which kind of shows how the d-axis current and q-axis current can be controlled and changed during the online changeover from 4 poles to 2 poles. So that is kind of a brief and quick overview of pole changing winding machines. During my work with Value and the University of Sheffield, we've filed a few patents on this kind of an approach. But there remains to be a lot more work to be done, and it's continuing to be investigated, not just at University of Sheffield, but at other universities and at other companies as well, as a potential way to electrify the markets, if you will, in developing countries where the infrastructure for full electric vehicles are still not available. So this was the work that I wanted to share with, as part of my presentation. Thank you, and I'm happy to take any questions at this point.
Dear Srinivas, thank you for your presentation. Yes, we have a question for you that just came up. What is your assessment of the technology readiness level? Can we see this in the market before 2030, or is that still too early?
So I think there are already induction machines for hybrid vehicles that are sold by Continental right now for their 48-volt architecture. And it is, I think in 2030 is actually quite further away. In fact, I think we should be able to see this in the market before 2025 for the hybrid vehicle segment.
Thank you very much. These are all the questions for the moment that came up to me. I assume that there will come more for sure after we start the panel discussion. So for the time being, I will just share your email address on the screen.
Sure.
Dear delegates, please feel free to contact him on his email address. You can see it right now on the screen. And I believe that we can move on to the panel discussion.
Sure.
So, dear delegates, speakers that I can see here in the system, please feel free to join the meeting. I see few speakers from now. Let me just add the speakers that I can see that are here. Just a second. Hi, Florian.
Hi.
Hi again. I'd also like to invite Mr. Castellini, who will join us specifically for the panel discussion. Hi, nice to meet you. And the rest of the speakers will join us a bit later because I don't see them connected. And dear speakers, you can see the panel discussions topic right now on the screen. It is gas oil price increase and influencing the e-motors technologies. Who would like to start to make a comment on this topic while we wait for some questions to come in?
I'm going to break the ice. Okay. So first of all, thank you for this opportunity. And it's really a pleasure to stay here in the panel discussion, mainly to share our thoughts on this topic that from my point of view is really actual. So basically, I want to start discussing this argument, taking one of the points that Jose showed previously in his presentation. Also, he mentioned that in 2011, we had a peak in the cost of the raw material, and this was really a big challenge for the industry. So my point of view is that right now we are in the same situation. So obviously the combination is even worse because from one side we still have a challenge in terms of raw material, and as is mentioned on the title of the panel discussion, we have also an urgent matter in terms of energy resources. So gas and oil prices increasing, is still fluctuating in a crazy way. And so this is going to impact the industry itself, okay? But this is what I have in my mind. So it will be interesting to discuss all together if this situation that in any case is objective, so we can not complain with this affirmation. So if this cost challenge, price challenge of the energy materials is impacting more the industry on one side, because it's clear that costs of the electrical machines, cost of the electric vehicles will going to increase, or it will be on the other side a facilitator for the electric vehicles, because it's going to impact on the other side on the standard combustion engines. I can start sharing, for example, my personal experience on that. Last year in September, more or less, I decided to change my own personal car. It was a Touran Volkswagen fueled by methane, and I bought my first electric car. So this was basically my personal choice. And if I have to share with you my outcome on this topic, I could say that it was more the second point of my introduction. For me personally, it was more interesting to push the electric vehicle markets, because in a medium and long time, I have foreseen a save of expenses for my family. And but this is, as I said, just to break the ice, and it will be interesting to hear your thought on that. If also maybe Florian, that had a lot of experience in different companies, feel this in respect of the challenge of cost increment.
Yeah, so first I bought my first electric car in 2015, and it actually was a Fiat. So as I mentioned at the end of my talk, the industry is getting a lot of influences to change continuously. And electrification is only one change of it. We see what I talked about, a software-defined vehicle. We're seeing autonomous driving. We're seeing electrification. All of this has influences from a lot of different sides, from the customers, from the the monetary decisions, but also from the availability. For example, here the oil and gas. And I think in general, it's naturally moving in certain directions. It just can go faster or slower, right? And so the current situation is actually accelerating the movement to more competition when it comes about electrification and the components of it. It's a little bit similar that we're all sitting at home for 3 years through a pandemic, and that has boosted video conferencing. Right, so video conferencing was about to come up anyway, but it had a significant boost due to some sad reasons. And I see similar things here that, as I say, the product and the market is moving in one direction anyway. It's just the acceleration or the influence can change the acceleration of it.
Okay, I've seen a comment popped up on.
Yes, there is a comment that just came from one of the fellow speakers. I will just display it right now on the screen. I would also like to say that Mr. Pai has joined us as well. I cannot see him, but I can see him. Okay.
Yeah. Sorry for joining late. Hello.
Hello.
You just came in time to see the question.
Yes.
Let me just display it on the screen. It's a longer one. It's a comment, not a question. So it goes as this. I think this fuel cost yields to increase the demand on the renewable energy solution as wind energy. This will increase the investment and in the wind turbine and wind generators and affect the investment in the motor generator industry. Thus, EV could get benefit from this renewable energy source. Any comments?
Yes, so I would say that, so in my opinion, each critical period, so in the history of the human being, he could, in some way, is obviously an opportunity, no? And so we have from one side something that is pushing us to find a new solution, a new way of life. And see, I can agree on this comment. So there's a trend, there's an opportunity also for renewable energies. That is anyway a sector where electrical machines have a huge part of the game, and I have more concern on the second part of the comment. So from my point of view, this is not straightforward in relation to the electric vehicles. So I believe that is true for the energy challenge, but is not exactly so well linked to how the energy will be used. So using of energy, from my point of view, is another story, is following other rules, and shortly is anyway an opportunity, but is not so clear to me that the two things will be linked in the near future.
Thank you for your comment. Anyone else would like to make a comment, or we can move to the next question?
Just a quick one. So I think in general, mobility has to be seen at large, right? So it's not just a car or just the motor of a car. You have to see the whole package. I mean, Tesla is famous for talking like mobility rather than building cars. But in general, I don't agree with Elon on everything, but on that one I do. You got to see the bigger picture, and you have to think about, where do I get my energy? How do I transport it to my vehicle? How do I store it? How do I use it in the car? And how do I get the best driving experience out of it?
Yeah, I agree on that. So just to share one of my experience in my working activity. So I design several models also for urban air mobility, and I agree on this comment. So the mobility is a wide package, so it's not just cars. And I believe that in the future it will be exactly wider than how we are approaching right now the mobility.
Thank you very much for your comments. I believe we can move on to the next question. It's a longer one, so again display it in two slides. And it goes as, how do we think Europe can remain competitive against the Chinese EV cars that have started flooding the European market? Customers won't have buying power like before, so quite a few will be tempted by these cheaper Chinese cars.
So if I may take the second part first, just to share some insight, because when we were starting building cars at Tesla and we were considering that exact statement, we were very surprised that that is not true. people are spending more money on cars, and they are spending more money on a particular upgrade in their cars. So we started to reduce the effort going into lower end prices. I understand this is not a broad spectrum, but in general, we've seen a lot of people who never bought a new car before, and then they bought our car and they did not buy the cheapest version of it. Most of them, when you go and look around, I just walked around here today. If you see a Tesla Model Y, it usually says dual motor with a red bar under it, which means that's the most expensive car they are selling in that segment. So it's very interesting to see that on a big scale, at least for the OEMs, because people who are short on cash usually don't buy new cars. They buy 10-year-old used cars. So new car buyers are actually pretty active and spending a lot of money.
Thank you.
Yes, I mean, in general, I think this question pops up a lot of times. How will the future supply chain, the future, competitor landscape look like in the car segment? And I think this is a really valid point because we see Chinese players getting more and more pushy. I mean, at least the local Chinese market already, this is so big enough that here, Chinese competition is really very dominant. I think it will be interesting to see how it pans out in Europe. But in the end, we have to understand that whoever offers the best performance at the lower cost, right, they win. I think there's nothing defeating that, right? So whoever understands this and offers the best performance at the lowest cost, they will win.
Yeah, it's the lowest cost per a certain unit. Cost, right? So if you offer the highest range for the competitive price, it's not the cheapest car, but it will be the lowest cost for X.
Yes,
I agree on that. It's a market, right? So it's the best performance overall.
Yes. And the second thing is also about branding, right? I mean, I guess BMW, even Tesla, Audi, Porsche, they all have their own customer base, right? Even if they are really expensive. And same with the iPhones, for example. I mean, they're expensive, but still they have a huge customer base. So even if some things are maybe expensive, they can always offer customers some selling proposition.
Yeah, interesting enough. Right now, I see actually that brand loyalty is a little at risk because I see a lot of people going around. People are buying a Polestar, even though they were driving Mercedes for most of their lives. Because now it's a chance for new players or for existing players with new products actually to pull people over and become your brand loyal.
Yeah, I don't know exactly how it works in the other states of the European country, but at least in Italy, so if you have a certain type of car, you show your status, and so I think that is like a Gaussian curve. So because we are anyway in an engineering environment, so we have to come back to mathematics, and so for sure someone will be tempted to buy a Chinese car. But I believe that the average of the curve, so the peak of the curve, is marketing driven. So the people, as I said, at least in Italy, will continue to follow the most expensive car. So it doesn't care about the cheapest one. So because if you have a car, a certain type of car, you can show maybe something in the community,
Status.
Yeah, your status, exactly. And on the other side, so again, is my opinion. So I think that we are in a post-globalization period, and so delocalization of the factories is not anymore a target for or a strategy for the big companies. So this means that production for Europe market will be mostly in Europe with the costs of Europe market. And on the other side, China in the future will be focused on its internal market that is going to increase, to become bigger and bigger. And I believe that at a certain point, the UE market for Chinese will be a sort of small bucket, not more than that.
So it's worthwhile to mention that also not every car coming out of China will be cheap in the future. Especially what we built at NIO, those were cars that were north of 80,000 euros. But they are designed for a different segment, for the luxurious segment. So there are high quality cars for a relatively high price, and this will change and more in the future as well.
Yeah. So at that time, just to make the discussion easier and bring a little bit, at that time, I would say that we have most to take care of the situation that we had in Italy 20 years ago, when someone was tempted to buy a BMW, acquiring directly in Germany because it costed less. So maybe someone in the next 5 years will go to China to buy a car that will cost less and drive back to Europe.
That would be a fun road trip.
Yeah, we together with the car, it will become also a YouTuber.
Exactly.
So can we move on to the next question?
Yes.
Good. Which is, how do you see e-vehicles holding their functionality and value over time, say 10 to 15 years? That is a big point in sustainability and effectiveness of electrification.
As an interesting point here is that the number of parts that actually can break in an electric vehicle are a couple of orders of magnitude less than in internal combustion engine car. I mean, you have only a handful of components who are actually in that. I know that the question probably targets towards the batteries, and we can talk about that separately. But in general, it's really hard to break an electric car.
Yeah, I agree. So the bottleneck could be the battery. Right now, I don't have the full picture, but in average, the warranty for batteries is 10 years. Right. And so this is for sure less than the target that the question is proposing. But also the battery technology is fastly changing. So maybe in the next coming years we will have for sure an improvement.
Yeah, there's also a lot of work going in to get something out of the battery after you take it out of the car. So usually no battery fails completely. It's usually a brick or a few cells. So there are two options I was talking to several people about. One is either, you have to pay, let's say a number, $10,000 for your battery, but you give the old battery back for $9,800 because 99% of cells are okay. Or another idea is floating is to just replace broken cells. So every time somebody comes with this crazy high numbers and shocking statements, it's about replacing a battery that's 99% okay.
Yeah. And also one thing we have to keep in mind is, there will be at some point of time ecosystem to recycle the materials from the battery, right? And just today I read somewhere on LinkedIn that it's possible today already to recycle 90% of the lithium content in the battery. And of course, also the manganese cobalt content can be recycled even better. So I think once electric vehicles become mainstream, I think most of these materials will be recycled. And second thing is, the batteries in electric cars, they have a certain life. But of course, after that, like Florian just mentioned, they're not really completely dead, right? So they could be used still, for example, for grid applications. where you don't have to really space is not so much a constraint, so you could live with large batteries having not so much capacity, but still maybe function another 5 years, for example. So these things will.
I know people who do that already. So
yes, yes. So I think the sustainability part of it will really gather mainstream when EVs become mainstream. I'm quite sure.
It goes a little bit back to my answer to the last question. You have to see it from a higher level, like a bigger scale. It's not just the battery of the car. It's energy storage that can be used in a car. It can be fixed, replaced, but it can also be used in a stationary approach.
Yes.
Thank you for your answers. And there has been a comment.
Yeah,
which I display right now. There was a recent news of a guy hitting 1 miles on a Model S, having to replace something like 8 motors.
Yeah, but that was 10-year-old technology. So, of course, it's not desirable, but the technology has changed significantly in the last 10 years. Also, Model S drivers tend to drive their cars fairly hard.
So there has been another kind of a comment, which just give me a second to display. At this moment, there is no way to recover, recycle, reuse the magnets from a PMCM motor in an economically feasible way. So that's something we have to work on.
Great startup idea.
Yeah, I would say that the economic way so far is a problem for the whole electric motor, not only for the magnets. Also, recovering copper is still a costing operation. So you have to put the e-motor in an oven. So we started the discussion talking about the cost of energy that is increasing. So is an open point from my point of view.
Yeah, as Lucas said before, I mean, this is how we work as engineers, right? There's a problem. Once the problem scales, so it makes sense to put effort in it, we will work on it to solve it.
So thank you very much. This was the last question from our audience. I'd like to thank each and every one of you. Mr. Castellini, thank you very much for joining us at the panel discussion. And very much we're hoping to see you very soon. As you know, soon there's going to be a hybrid version of the event in March, as far as I know, in 2023. And we honestly hope that we will see each and every one there, as well as our delegates. So thank you very much.
Thank you to you. Hope to see you soon. Have a nice weekend.
Bye.
Yeah, thanks to you too.
Thank you. Enjoy your weekend.